Let's take a look at a practice problem dealing with the stuff we've just covered. We're going to look at interference from two sources. The question we're going to look at is, if we have 2 point sources that are generating periodic waves in phase, meaning they start off with the same wavelength, they're both going up at the same time when they're both going down at the same time, and the wavelength of each of these is 4 centimeters long. A point on a second antinodal line is 30 centimeters away from the nearest source. So we have a second antinodal line 30 centimeters away from our nearest source. We want to know how far is our furthest source away from the antinodal line, the same point. So let's begin with a sketch. So in my little basic sketch, I have 2 sources, one here, and the nearest source to a point, an antinodal line, a point on that antinodal line is 30 centimeters. I want to know how far is it to the other source. So I can go through and I'm going to try to solve for L. Well, the point on the second antinodal line means that we're given m equals 2. So if we're given m equals 2, I know something about this. I know that my path difference between them is equal to 2, my m equal 2, times the wavelength. And since my wavelength is 4 centimeters, I can take this and go m times their wavelength. 2 times 4 gives me 8 centimeters. So the path difference between these 2 lines is 8 centimeters. Since I know this is the shorter of the 2, this L has to be 8 centimeters longer than this guy. So I just add them together. I get that L is equal to 38 centimeters. So it's 38 centimeters from the furthest source, and that's what our answer is. So pretty straightforward, basic thing. But again, back to the idea of, do you have how many number of wavelengths are you different? What's the difference of the path length? It has to be proportional to the m times the wavelength. So let's try another problem. It's just kind of the same problem, but worded in a little bit of a different way. We have 2 point sources generating waves in phase, and the waves have a wavelength of 3 centimeters this time. At a point on the nodal line, doesn't say which one, we know it's 25 centimeters from one source and 20.5 centimeters from another. So let's construct a sketch and see what we get. Well, my short one is 25 centimeters. My long one is 25 centimeters, so 20.5 and 25. Again, the difference between the two is going to be my path length difference. So my path difference is found to be SP1, my first path length, minus SP2, my second path length, and I get a total difference of 4.5 centimeters. I used absolute values because I don't know which one's on the right, which one's on the left. But it's 4.5 centimeters difference. Well, the 4.5 centimeters difference, our path length difference, has to be equal to m times the wavelength. So if my wavelength is 3 centimeters, and my path length is 4.5 centimeters difference, I figure out what m is, and I see that m is equal to 1.5. So they vary by a wavelength and a half, which means that they're on the second nodal line. They're not on the first, because if it was the first, it would be 0.5. It's the second because it's 1.5. So our answer is our m value is 1.5, or it's the second nodal line, or the second destructive interference line. So we can do further problems like this, and there's a lot of different ways we can ask these questions, but they really come down to what's the path length difference, how far do you have to travel. You know, some of the variations I've seen on this problem is what's the difference between these two, and we'll start to get into why that's kind of an important question, or what angle does this guy appear at. All of these are further questions that we can answer, and actually this is really where it's going to get into some interesting physics, is when we do ask these questions for light interfering, which is our ultimate goal. So again, m equals 1.5.